This presentation will cover the second topic of the first chapter, which is motion in 2D. This presentation is on uniform circular motion. The following learning outcomes as required by SACE will be covered in this presentation, so you can pause the video now and tick them off in your book. The formulas in particular, though, will be covered in more detail in an example video. So as an introduction to uniform circular motion, it is important to review vectors and scalars. So if we remember, a scalar is a quantity that has only magnitude, and a vector is a quantity that has both magnitude and direction. The example on this slide refers to speed. However, acceleration is also a vector quantity, meaning it requires, or it has, a magnitude and a direction. Okay, so what we're going to try to do is explain uniform circular motion, the definition of it, and link it to velocity and acceleration. So let's take a Ferris wheel, for example, and let's look at the carriage marked in red there. So the Ferris wheel is rotating at a constant speed, and at this location, its velocity has the magnitude of that speed, and its direction is out in this way. When the carriage is, say, on this side of the Ferris wheel, it has the same speed, but its velocity would be that way. So it's tangential to the motion. Okay, so what this means is, although the speed isn't changing, the direction is, meaning that the velocity is, because velocity, remember, also velocity requires magnitude and direction. So if one of them changes, that means the velocity is changing. Okay, so throughout this presentation I've got a few shockwave files or animations in the slideshow that don't quite work with the program that I'm using, so you can't see them. What I'd like you to do is pause the video, open up the actual PowerPoint version of this presentation, and open it up in presentation mode so you can click start and view the animation as it goes. Okay, so this animation in particular on this slide, it shows the velocity of an object as it's traveling in a uniform circular motion. So this person, for example, if the person's in this location, the velocity will be tangential to its path. Okay, when the person is over here, the velocity will be out this way. When it's over here, the velocity will be out that way. It's always a tangent to the circle. So as previously mentioned, although the magnitude of the velocity doesn't change, the direction of the velocity of the carriage changes in the Ferris wheel. Now, by definition, a change in velocity indicates that acceleration is present. Therefore, we can say the carriage is accelerating. So we know a body in uniform circular motion has acceleration, but what's the force that causes this acceleration, and which direction is it in? So we know the acceleration must be perpendicular to the velocity. This is because if it wasn't, the velocity would be increasing or decreasing. However, the magnitude of it is staying the same, it's only the direction that's changing. And this direction must be pointed towards the center of the path or the center of the circle. So looking at the diagram on the left, the direction of the force, or the direction of the acceleration, is pointed towards the center of the circle, when the object is following the path denoted by the black line and with the velocity of the red arrows. So a couple of summary dot points on this slide. The acceleration does not change the speed of an object, so it doesn't change the magnitude of the velocity. The acceleration must act perpendicular to the object in this case when uniform circular motion is occurring. The velocity of the object undergoing uniform circular motion will be tangential in direction to the circular path. If the object had no acceleration, it would continue in a straight line. To keep going in a circle, it must be pulled back to the circular path. The acceleration that is experienced by a body in uniform circular motion is called centripetal acceleration. So again, in this slide we have an animation which you'll need to refer to the other copy of the presentation. But this slide indicates the direction of the acceleration as a body moves around in a circle. So the arrow indicates that the acceleration always points towards the center of the circle when the object goes around. So using Newton's laws to explain uniform circular motion, Newton's law states a moving body continues to move with constant velocity unless an external force acts upon it. So because the carriage is not moving in a straight line, there must be a force acting on it. So Newton's second law states that F equals ma, and this means that the carriage has acceleration. In our particular case of the Ferris wheel, the force that causes the acceleration is provided by the arms of the Ferris wheel that are connected to the carriage, and it's actually called the centripetal force. So one of the SACE requirements is for you to be able to identify where the force comes from when an object is in centripetal motion. Okay, so an example would be when a car is traveling around a circle on a track, the centripetal force comes from the tires of the car and its interaction with the road being a friction force. When we swing a bucket of water around our heads, the tension force in the string provides the centripetal force. And another example would be when the moon orbits the Earth, the gravitational force between the two, provides a centripetal force. This is another slide with an animation. In this one it just shows a car traveling around in a circle with a velocity vector, which is always tangential to the circle, and a direction of the force vector, which is red, always pointing towards the center of the circle. This animation also gives you a top view, which can help further explain this. This is another animation where the Earth orbits the Sun. Now, although this is not a contact force, the force of gravity is still present, and that is the force that provides the centripetal acceleration. Okay, our first formula for uniform circular motion. This relates to the magnitude of the acceleration and its relationship to the velocity and the path it's taking. So the formula is given on the screen, where A with the subscript C denotes the centripetal acceleration, V is the speed that the object is traveling, and R is the radius of its path. Now the direction of acceleration is along the radius towards the center of the circle. Now when we talk about an object when it's moving in a circular path, we can talk about its period, and this is denoted by the equation given on the screen. So the period is given as denoted by a capital T with the units of seconds. V is the speed of the object, and R is the radius of its path. Okay, in this animation, which will work on your version of the presentation, we have a blue object that travels in a circular path, and what you can actually do is toggle the mass of the object, how fast it's going, and its radius, and you can see the red force vector and the size of it representing the size of the force and how it is impacted by those three variables.